Okay, so let's get started with this year's version of the panel. We're going to start with the high NA question, right? So, high NA and curvilinear are both big topics, but we'll start with high NA. So 80% of those surveyed believe broad adoption, which means more than one company, right? Will occur by 2028, and that's about the same as last year. The industry collaboration to make EUV successful has been really amazing, and High NA is definitely going to continue that. But there is a question now about large format masks, so wanted to ask about that. There was a session on Sunday that Frank Abud arranged that talked about 6x12 masks, and Mark Phillips was pretty convincing, as he always is, that there's reasons to do it. Maybe, Harry, you can start us off with pros and cons of the 6x12 mask, kind of a summary.
Yeah, the biggest pro, I think, is productivity. When you go to the, say at the 6x6 reticle, you now have a field size that's half the distance in the scan direction. So you have to scan a lot more times, and it's more than 2 times. And so we're seeing estimates of 15 to 40% reduction in productivity from tools that cost $400 million a pop. So there's considerable motivation to try to do something, because you can save a lot of money there that you can now spend someplace else. The cons is sort of every tool in the involved with mask making, mask measurements. Now you need a new copy with that'll handle a larger substrate. There are other challenges such as the pellicle and so forth. It's a long list, so it's a big challenge. But we are talking big money when it comes to the productivity loss on very expensive tools.
It's big money on both sides, right? Glenn, what mask makers gonna do that?
Well, Aki, I think on the memory side, we never get to half field sizes, right? We're fitting more than 30 die per field, and we can stitch these together. So we're stitching it together with what's called an AA stitching method, where we're going to be on the low end of that quote that Harry just gave. We'll be on more of the 10 to 15% productivity loss. So it's difficult to see that would really be economically viable on the memory side of the business. But I definitely appreciate what Frank was saying on the logic side. If you have very large half fields, you can get 40% gain on a very expensive tool. That should be looked at.
Yeah. Chris, your opinion as a merchant mask maker, maybe?
Yeah, so I guess the round mask was an interesting idea. We kind of liked that because you could leverage wafer tools. Then I guess ASML decided they were too heavy, so that wouldn't work. So we went to 6x12. I think we should launch a design study on a curvilinear shaped mask substrate. You could optimize the magnification. The productivity benefits are, obviously clear. As a merchant mask maker, we make lots and lots of different kinds of designs. We did one little study where we surveyed about 3,000 designs we built over the last some number of years, and we see how they would fit in a half-field layout. And very few chips, at least one instance of the chips, didn't fit. I think we had one design that was too big. But what we did see is the packing density was really poor with the half field. So the mask gets full at 4x, about 85% most of the time on average across these 3,000 designs. When you go to half field, the packing density only goes up to about 65%. So it's really worse than it sounds. The instantaneous field size is half in one direction, and your ability to use that goes from about 85% down to about 65%. So it is a major productivity hit for sure, particularly for a company that makes foundry masks and lots of different designs. The question is just the cost. It's likely cost prohibitive for merchants to do this, but the need for the end users is quite clear. Yeah, it's an important thing. I guess the last thing I'd say is we also make masks for flat panel display. Those are these gigantic rectangles. And We learned a few things about handling, wildly asymmetric substrates. The developer on that looks like a car wash, actually, when you go through. It doesn't look anything like developers we have today. So we learned a lot of things, the difficulties and challenges with really grossly asymmetric substrates. Even simple things like EBR, asymmetric pileups, lots of stuff. So not just building the tools, there is a lot of process learning that have to be done across the industry to use an asymmetric size substrate and hit the uniformities that we've all been accustomed to. So
Those 80-inch screens are all one-to-one dimensions.
yeah,
right?
that's all 1x. That's why they're so large. But we have some masks called long masks, and they are, like the size of this table, literally, in X and Y. And they're spin coated, believe it or not. But it's you don't want to stand near that thing. So.
So I guess there's a mixed opinion, right, on 6x12 masks. Let's switch gears and talk about the minimum mask dimension. So what's the smallest thing we're going to be asked to write on a high-NA mask? That's probably about like SRAF sizes or something. Chris, you want to, yeah.
So I guess for the standard at the low NA, whatever we're calling it, I think 24 nanometers seems to be kind of the sweet spot everybody is converged on. And that's clearly a useful SRAF size. We did a talk on that today, and I'm sure many others have as well. So there's value in a SRAF that size. Maybe small, but if you just scale by the NA in one axis, that would get you at high NA down to about 20, just scaling it down. Mm-hmm. So I think it's logical to think 20, slightly below nanometer SRAF is going to be useful for the patterning and the lithography. And I don't think the front end is the challenge with that. I think the writing and the resists and hard mass and things like that will be able to make those size features. I think the back end is more challenging, repair, inspection, all those things. So scaling the SRAFs well below 20 is, I think, a bigger back end challenge than it is.
So you, like from a lithographer perspective, your former life, like it would be useful.
I think
to
it would
have
be
something
useful,
listed,
yeah, especially for the through focus effects, as a small pitch through focus, best focus shifts and all. I think definitely it's useful to have them that size, yeah.
And as a mask maker, you think you can do it?
You can do the front end. I think we would be more concerned about the back end process, an efficient, productive back end process to do 18 nanometer SRAFs. I think that's hard. But the patterning, I think, there's clearly a roadmap to enable that.
Compared to today's sizes, it's a little small. No? Go?
Oh yeah, I think no doubt the patterning challenges on EUV, even low NA, when we get to high NA, are just going to continue down this curve of getting more and more challenging. And this kind of result, probably not surprising. It's a little bit hard to see this early exactly how small DRAM patterns will require. But when we look at curvilinear shapes and how tight those curves are going to need to become in order to perform, either extend low NA or perform on high NA, is still TBD. And I do think one advantage of high NA as a mask maker that we may get is this y-axis extension going to 8x in y. We may see a little bit of relief there, even as x becomes tighter.
Mm-hmm. Yeah. Harry, how about looking at it from an OPC perspective?
Well, I think one of the interesting part is we are now using a lot of negative resists for metal layers. And the net is that your SRAF is going to leak light down that can actually leave resists behind. I mean, before when you sort of get a printing SRAF, it was kind of a nuisance. You got a little bit of a divot in the resist, and as long as the resist was thick enough, you didn't punch through during etch. But now you're going to leave a real defect behind. And that's not speculation. I think we had a presentation on that sometime in the past year. So, that's a concern.
Thanks. Yeah. Okay, let's go to the next topic. So multi-beam writers, and I think the luminaries' answers are pretty clear that multi-beam is good for EUV, but I kind of wanted to explore why that is. Why is it that people think that multi-beam is more precise than VSB writers and that it's necessary for EUV masks, whether it's Manhattan or curvilinear, is what it says. You know, Glenn?
Yeah, definitely multi-beam is being used not exclusively for EUV, but EUV is exclusively on the multi-beam. And the reasoning you're seeing that is the low sensitivity resists that are required to get the type of LCDU that's needed for the patterning. Just generally any type of line edge roughness, line width roughness, we see local CDU effects that translate onto the wafer. We need that lower sensitivity resist, and you need the multi-beam to enable that. And then curvilinear patterns. As we introduce OPC for curvilinear, that also applies to EUV. And of course, the only way to print that with a very good resolution is to use a multi-beam. So I think those two factors really drive the industry there, and both of them are required for EUV.
Harry, did you have? Yeah.
Yeah, I think Glenn got the salient points there. Certainly, you need a high dose to print a nice line with good CD control and low LER. And yet, but now, of course, you're going to put a lot more electrons into your substrate. So doing that in a distributed way, so you sort of don't localize the generation of heat, can be sort of yet another benefit. So multi-beam writers are good things.
Yeah, multi-beam spreads the electrons more, right?
Yeah.
Chris, yeah.
Yeah, I think the colleagues hit on the points. You know, it gives much better overall edge placement control on the mask than you can do with VSB. It's a combination of the high dose resists and the way the electrons are distributed in the films. Those two things kind of conspire together to give you a generally much better edge placement control, and that's valuable in mask making. You know, the other thing for commercial mask makers, and I guess it's for everybody, is the flexibility of the tool, going back to rasterization in the writing, predictable write times, the way you control the line actually is quite simpler with a multi-beam because you can have predictable writes. And there's a lot of flexibility and programmability in it, and that's very nice when you're trying to optimize, mask process for many, many different design styles. So all those things, I think, make multi-beam a more effective tool for mask making.
Yeah. That's why Elmer's company is worth $4.3 billion this year. So let's see. Staying with the EUV theme, Glenn talked about pellicles a lot already, but we did ask them, what they think about the need for number of masks if you didn't have pellicles, right? So clearly, if you don't have pellicles, that's going to fall on it. And what's the number? It seems like 2 would do it, right? Because you have one, you clean it, and you have another one. But apparently, that's not what everybody thinks. Do you have any insight on this, Chris?
Well, I mean, I was a little surprised at the 10 or more. I don't know if people are they're just losing the masks or what's going on there. But,
where did they go?
I'm not sure. Unless that big number includes, the need to do respins, for example. Maybe there's more uncertainty in the validation of an EUV mask, and so folks think they're going to have to build more of them for that reason, nothing to do with pellicles per se. But the lower numbers, I think, just as you said, it's correct. You would need a couple in circulation because without pellicles, they're going to have to be cleaned more frequently. There's lifetime issues and things like that. So you're not going to let a lithography line go down, sit waiting on a pellicle. And we've seen this before, even with DRAM fabs in particular that are just ramping. It's not unusual, because they don't want anything to stop that, to have multiple copies of mask sets going in at the same time. So the 2 to 3, not surprising, but I'd have to leave to my colleagues to tell me why someone might need 6 or 9 masks.
I can tell you, Chris. So 10 or more, we even see it on optical with pellicle that we can have 10 or more copies on the memory side running at once, just because of such high volumes that can happen on parts that have ramped. So it's possible that if we get to a point of an EUV ramp, we will easily see 10 or more. But I'll tell you, for this year, this particular year, we're probably still in the 2 to 3 range, given it's a down year for memory, and this is specifically to EUV. But there's going to be factors that even go beyond just saying with pellicle or without pellicle. I mean, even running with a pellicle, you still have to have many copies. There's a significant risk of pellicle damage that could occur inside the scanner. It could occur out of the scanner and take out the mask. And for those reasons Chris mentioned, these high-dollar scanners have to be maintained. They have to keep running. And we need the ability to swap one reticle in and one reticle out. And of course, like optical, we're already seeing the beginnings of customizing EUV reticles per scanner, where you can tune the registration for a particular mask and put it on a particular scanner, and that's the only scanner it can run on. Mm-hmm. So you want to release a layer, you need to have a second copy, and then copies of those copies to support volume. This is an exciting area.
When you say 10 or more sometimes required for even ARF, you mean like because you have multiple fabs and you have multiple lines, or you mean?
Even within one fab, you could have multiple scanners and just so much wafer volume that you need to have many copies running simultaneously.
So I guess a reasonable question then is, like, for EUV equivalent in the same volume, would you expect like 2x or 3x?
I'm going to expect a higher quantity, absolutely. Higher than what we see on optical, whether with or without pellicle.
Harry, would you expect the answer to be different for a logic maker?
Well, I think with the lower volumes that you get, at least in the foundry, typically you do have different. The considerations are a little bit different. I think it's the one is just how long can the reticle be being used in the scanner before it gets dirty, and that's a dynamic situation. A number of years ago. Remember, people were telling ASML that you were rapidly getting dirty reticles, which was contrary to all their testing. And then it was discovered that the thing you needed to do was turn the light on. And that actually generated plasmas in the hydrogen that's in the reticle stage area that significantly, basically it charged up the mask, charged up the particles, opposite charges, and now they're attracting. Some really excellent engineering by ASML to figure that out. Really kudos to them. So it's a dynamic situation and improving. If you can go a very long time without it getting dirty, you're good. But then the other thing is, how long does it take to clean and qualify a mask? And do you, if it has a particle on it, when you clean it, does it come off the first time? Do you not add something else that time? So again, I think a lot of this is dynamic as people improve their tools and processes. But I think sort of probably a minimum of 3 is needed to have uninterrupted flow of a product that you're running on a regular basis.
When you clean the mask, like, doesn't it break sometimes and stuff? Or, no, it's a safe process.
Well, part of it is it's chemical, and you are always going this balance between having chemicals that are harsh enough to remove particles, but not harsh enough to damage your mask. So after a few times of getting cleaned, you do start to remove material, and there's a number of cleans typically, that a maximum number of cleans before you have to replace the mask. So,
is that like breaking of masks an issue during cleaning? Well, it's okay.
Just degradation, like reflectivity changes and things like that.
And then you re-inspect, you recall, right?
Yeah, particles that don't remove can be a problem with cleaning, or particles that get added, but actually physical breaking, I don't think.
Not like that. But
yeah. I'll make one more comment on this that I think is quite interesting for the mask maker. When you start getting up to a lot of copies, and you're making 10 or more copies of a given layer, it also presents some opportunities. It presents opportunities for us to really dial in our CDU and our registration and really tune these reticles. When they go through very fast and it's a one and done and you don't see that particular pattern again, you can give it your best process right from the start. But when you get a chance to do copies, particularly in short succession, I think there's going to be opportunity there for us to get even better process control.
Yeah, sounds good. So yeah, that's why you need many of these multi-beam writers to be
Yeah.
able to
Apparently.
to write these masks, right? Okay, so going away from writers, actinic inspection and also some other inspection methods. Glenn, maybe we can, because you talked about this a little bit, tell us about inspection, tell us about requal.
So, yeah, that's a good question, Aki. I think reticle requal in the wafer fabs, and I sat through a number of presentations at this Bacchus conference. It looks like 193 still has a lot of life left in it for the purpose of requal. Even if the pattern can't be completely resolved, for requal, we're really just looking for adders into the pattern. And if we can reduce noise in the imaging and see those defects, even if you can't get a good optical image of it, you know it's there, you can disposition it to clean or particle removal and get the mask back into service. For the mask maker, it's a different challenge. It's not just requal and particle detection, but we actually have to detect pattern defects. We have to resolve the pattern. I think it's possible 193 still has a place, but eventually to EBMI and APMI, they have to come on board as the pitches shrink.
Chris, because you're a lithographer, right? You know, inspection is taking a picture, but you don't need, in requal, you don't need to resolve it. You just need to know something is wrong, right?
Yeah, I mean, to a degree, you need resolution that's consistent with the size of the defects you're looking for. But you're right, you don't have to resolve them in fine detail. But I think, the actinic, it gives you resolution for sure, but also any defect that's mixing effects between the multi-layer and the absorber, you just don't get, you might be able to, it might show up as a defect on a 193 tool, but the dispositioning and the classification problem is really much more difficult. So I think the actinic gets you two things. It gets you the effects of the mixing of the multi-layer effects with the absorber, and it also makes the classification of the defects, which ones to repair, all the productivity, the entire back end, much, much smoother if you can inspect actinically. There's no question about it. I mean, I think for a commercial mask maker, the problem is actinic EUV is only really good for one thing, to inspect EUV masks. And if you don't have the volume, you've got to, it's the point Glenn made, you've got to spread the cost of a very expensive inspection tool over very few masks. So probably, if it can work, an E-beam based inspection, if you need the resolution, E-beam based inspection, probably a little better for commercial mask makers. At least you can use it on 193 masks. It's just more fungible across different product types. So combination, I think the ROI probably is better with that, and then using AIMS and things like that to sort out the substrate effects.
So multiple solutions, right?
Yeah.
Okay, let's shift gears again. This is about the cost one. Glenn already addressed a bunch of this, but I was personally surprised with the OPC MDP one. MPC gets easier. That's really? Is that true? Harry, do you have any insight into this answer? How did you answer?
Well, I think that the problem is the computational lithography aspect of EUV is a complexity of a level we've never experienced before. And it's just going to get worse over time. These mask 3D effects are one of the reasons we can't go to as low K1 as we'd like to with 0.33 NA. And they're seriously going to limit what you can do at 0.55 NA unless you find computational solutions and perhaps a new mask absorber. So this is, I keep thinking back to the day when, Peter Silverman of Intel, stood up at a conference. He said that one of the great things about EUV was we wouldn't have to use OPC. And of course, his
It was once true, right?
his company's roadmap at the time was to insert EUV at the 45 nanometer node. So that is absolutely correct. But it's.
So do you think maybe that's like the leftover effect, maybe? There's some expectation that EUV is so high resolution that you don't need to do any OPC, IoT, and therefore MDP and MPC is much easier too. Like you just like print the same. Actually, 7 nanometer, there are some of that, right?
I'm really surprised, actually. I mentioned Silverman of Intel, but there was, in 2001, a paper from someone else at Intel where the best focus was plotted as a function of pitch. And it showed that certainly for the dimensions of the 45 nanometer node, there's like a 5 nanometer focus difference. But as you went to smaller features, it just fell off a cliff. Mm-hmm. And those data have been out there since 2001. So in some ways, I'm kind of surprised that more people didn't look at that curve and start to worry a lot earlier. So.
Glenn, yeah.
Well, in addition to the things I mentioned in the presentation, I mean, one I didn't mention, but does have a big impact on cost, and that's just the very practical equipment uptime and managing equipment, the advanced equipment, particularly EUV equipment, at least to the level that we've been able to achieve on optical. Because if we need to start having redundant equipment and multiple pieces of equipment due to lower downtimes or higher downtimes, that adds up very quick. Outside of that, Aki, I think materials management, there's opportunity to avoid defects and integrate how we're avoiding defects further up in the supply chain that could bring cost efficiencies on the material side.
Mm-hmm. 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 Anything from your perspective on the cost stuff?
Yeah, I mean,
I
think the chart kind of says it all. It's going to be a very expensive mass technology. Yeah. And if you look at the capital spending on photomass over the last couple of years, it exceeded, $1.5 billion. That's a capital intensity of about 40% of the size of the mask industry. The typical semiconductors runs around 20. Mm-hmm. Mask industry spent close to 40% of the size of the industry on capital equipment. So that is an enormously higher capital intensity, even than wafer fabs. Mm-hmm. That was mostly to tee up first generation EUV. High NA is going to have another swing that's going to look like 40, 50% capital intensity. So there is no way you just simply wish those kind of costs away. I mean, it's a technology right now that's tailored for very, very expensive, high margin chips that are high runners. And that's really what it's going to work. And that's the box it's in. And sure, you can tune things and lower the costs and work on it, but it is by nature a very, very expensive technology. Mm-hmm. And even if you look at units, if you look at the Tech Insights number for EUV mask units, it's the fastest growing, but only about 7% of total mask units by 2027 of total ship. Mm-hmm. So that means all this cost has to be amortized over 7% of the mask units. So, that's the nature of it. So you need the right chip, and you got to make a lot of them for this solution to make sense.
But apparently there are.
Apparently there.
I remember actually in the lifetime of the E-beam initiative panels, and I remember there was once where it was just taboo for me to ask a question that suggests that masks were going to be more expensive. Like somebody would just yell and say, "No, masks have to be cheap."
That was the $1 million mask set. Remember that? Now we've got the $1 million mask. So.
Yeah. So I think some of it is like all this AI stuff, right? And when you need 30,000 full reticle H100s to do ChatGPT, and everybody else has to copy that, right? That it consumes a lot of this stuff, and they're willing to pay a lot. So. Okay, so let's see, non-EUV leading edge. So I talked about this a little bit in the beginning, but let's say there is a 193i leading edge, right? And there's talented people that are now available to work on that leading edge because that company doesn't have EUV, right? So their leading edge is this. So the question is, how far can we drive down 193i without EUV? Obviously, it was possible to get to 7 for some people, but it might not be economically viable for people that are not doing EUV, right? So that's the question. What do you think? Do you have theory?
This is the extent, just 193, how far?
How far can
Yeah,
193i go down?
Yeah, I mean, those, 7 nanometers seems a reasonable sort of thing, but the node definitions get pretty diffuse when you start to get into that 7 to 14 nanometer regime. So, to do
Well,
a
actually, do a
fully
28,
scaled 7 nanometer shrink, all optical, I mean, I think it's doable, but I think more likely what you'll see optical able to do is extend it a couple layers, like shrink a contact layer or a specialty design, make a few layers much, much better, and in that make a higher performing chip. So you'll see selective shrinks, probably even below 7 nanometer.
Even below 7.
Yeah, I mean, we have customers. If I can get this one layer to look like a 5 nanometer node, it carries along the performance because of the way I'm designing it for a lot of other functionality. So in that regard, yeah, 193 has a very powerful role in extending capability into that regime that's shown there, I think.
Well, I don't think DRAM is going to do this, but maybe some of your foreign competitors might do something. Do you have any opinion on this?
I think 193i continues to develop. We see even curvilinear being applied to 193i, low sensitivity resist being applied, multi-beam being applied, and the mask making on 193i continues to drive and be pushed for improvements, particularly around registration. So it's a very active area of work right now, even within Micron and within the mask shop, to further develop and push the technology. And if there is opportunity to avoid converting levels over to EUV, and it makes economic sense, we want the 193i capability to do that. So no give up here. I think they're all going to migrate together.
Well, so it's not like now that you have EUV coming online, like you're just going to do it with EUV. If
Correct.
you can do it with 193i, with all these different tricks, with RET or whatever, you're going to do that.
That's exactly right, yes.
Okay, that's interesting. Harry? Yeah.
I mean, I think that using optical lithography, there's a lot of exciting things happening there. There's a lot of the technologies when we first put them into production, say 90 nanometer or 65 nanometer, we buy state-of-the-art tools and we could achieve a certain capability with the resists available at the time, but everything's gotten better. And it really, I think the discussion has to be, are you talking about using your legacy tool from 1995, or are you going to buy a new 193 nanometer tool today? Because Zeiss has learned a lot over the years, and without a lot of effort, the aberration is going to be a lot lower. So, so I think that you could do that, and we've all been talking about the pain and the costs of EUV. So there are a lot of things you can do to do shrinks. And there's some other things that are happening out there. So, for example, the quantum computing people need just outrageously low levels of line edge roughness, but they don't make small features. So there's a lot of work for good engineers to make a big impact on various things without going to that 100 billion transistors on a chip. So there's a lot. Our industry really has become dynamic across the board in recent years, and it's fun to watch.
Yeah, 100 billion transistors on the chip. Pretty amazing, right? I mean, what this industry does is pretty amazing. Okay, so let's go back to what's going to happen in the overall investment. Like, what's going to where is the spend going to increase is the question. So inspection is one, multi-beam is one, and then what's going to happen to VSB? 31% of the people still say, it's going to increase. VSB spend is going to increase, right? And laser mask writers, we heard a lot about that today in Matsuno's session. What are your thoughts about these? You want to comment, Glenn? Yeah.
Sure, I'll comment here. So with so many fabs coming online and just general mask volumes increasing in the second half of this decade, it doesn't surprise me that E-beam, multi-beam mask writers are number one on here for overall investment. It's just really the direction that all the critical levels you could say don't require, but there's definitely a preference to write on the highest end tools that we have available. And when we're looking to buy next generation tools, I mean, you do need to consider what kind of volume you're bringing online, but if you have flexibility of the kind of capital that you're putting in that can run both lower end and higher end, you'll almost always default to the higher end. So I think this is interesting, but not surprising.
Yeah, default to the higher end as long as it's compatible.
Correct,
Right?
yes.
Yeah. Chris, you want to comment on this?
Yeah, I think just second what Glenn said, not that surprising. The laser writer industry's been interesting over the last couple of years. I mean, Micronics did a nice presentation today. They entered into it, sold more than 40 tools. So clearly there's a lot of pent-up demand for laser writers there, which is kind of interesting. Just those 40 tools I calculated puts about 150,000 mature mask units into the system. That's a lot of mask units, and they're still selling tools, and they've also energized, I think, their laser writer competitor to sell more tools also. So, I have to assume that a lot of the heavy sales of laser writers are to replace end-of-life tools, aging E-beams and things like that. So the demand will go up, and it's really interesting now with access to high-quality laser writers that are fast, some of the uses for those in mainstream applications, being able to make curvilinear shapes, new kinds of designs and things like that. So I think it's a good, that's a positive trend, and that number also doesn't surprise me. You're going to see big increases.
So the laser writers, some of that replacement is the old VSP writers.
It has to be. I mean, it's just the world just doesn't need that many more laser-written mask units. So I think 50%, if I had to make a wild guess, 50% of those is to replace end-of-life tools, old cores, E-beams that are dying that can be done with laser writers. So it's a pretty good balance. But there's a lot of new capability for laser-written masks now around the industry, and I think people will figure out how to put it to good use.
Yeah.
I would also question some of this too, Aki, like on the VSB writers and people saying that it might increase. It's not completely clear that everyone in the world would even have access to purchase multi-beam writers.
That's true.
So you could have some people responding in this manner just because that's what's accessible to them. And for that purpose, we'll see this for a long time.
Right, right. So geopolitical situation.
That's right.
Yeah. Harry, do you have anything to add?
Yeah, I think this question I think was asked before we found out that this sort of lower cost multi-beam tool is being installed at the AMTC in Dresden.
Flex, yeah.
Yeah, and so I think that is that's intriguing for a lot of reasons. I mean, ASML basically came to dominate the exposure tool market by selling the most expensive tool, but their throughput was so much higher that the actual cost per wafer was lowest. So we'll have to see what that trade-off actually turns out to be. And the other thing is that for some of these older, we talk about how do you make use in your fab of optical tools and not go to EUV. As you well know, curvilinear features is a very nice approach. So now we're going to have expanded need, I believe, for writing curvy masks, but not EUV masks. So I'll be staying in good touch with my colleagues in Dresden, and it's going to be very interested to see how that turns
that's right.
out.
You used to work with them, right? Yeah. Okay, so speaking of that, curvilinear masks, there's a bunch of questions there, but you talked about it a lot, Glenn. So curvilinear masks are here to stay, is what this says. You agree?
I agree. They're here to stay, and some of the challenges in your graph there on the upper left around mass metrology is significant. We definitely see challenges in measuring these curvilinear features, finding the centering of these curvilinear features, and just the quantity of data that we want to be able to collect on the mask to correlate back to the wafer and start to study even subtle effects within the patterning Takes a lot of tool time and engineering resource as well.
I used to think, like, what's the big deal? You just do the, you just do the EPE instead of, you don't have two parallel lines that you can average over. But if you just EPE and average it over, like, isn't that good enough? But somehow that's not enough. Right? You need a definition of goodness or something.
That's right, a cleaner definition of goodness and how we qualify these masks with high volumes of measurement data.
Yeah.
So we could really see subtleties that are going on,
Yeah.
much like they can now do higher volumes of wafer measurement data and how that can translate back to mask.
Right. So Harry, the same thing goes for MEF definition and stuff like that, right? Yeah. It's like you need a curvilinear definition of MEF and other metrics.
Yeah, I mean, the implementation of Curvy is going to take a while. It's pretty complicated. I think most of us took Euclidean geometry in high school, and that's enough to understand rectangles. But when I start to look at the math that just involved in trying to characterize curvilinear shapes, it's their graduate level college, graduate level math. It's a big gap. So it's going to take a while, but this industry has so many smart people, it'll get figured out. But it's definitely not simple.
Yeah. Chris, what do you think? Do you think curvilinear masks are going to extend all the way back to like laser-written masks too?
Yeah, I think a lot of things that are developed for cutting edge sometimes don't port very well to prior nodes, prior applications. But curvilinear, I think, has a good chance for trickle-down benefit for sure. Yeah, and so we already have a couple projects going on using laser writers to do curvy features, and Harry mentioned the Flex tool that's given a multi-beam tool accessible, really, that was designed mostly for merchants, a way to do more economical curvilinear shapes. And so I do think this has a high trickle-down advantage. Fab extension projects, new types of designs that are generated in different ways. My colleague talked about that during the mature session. So yeah, we're more optimistic than we were that this would be impactful to mid-range and mature nodes as technology.
Mm-hmm. Yeah, great. Yeah. Thank you. So we're just gonna finish our part of it now. I always ask at the end of a panel what you think about the future of the industry. This year Jan talked about semi saying a little bit lower, right? The luminaries are saying no, it's going to be okay. Like where do you sit on this year and future going forward? Go ahead.
Yeah. I mean, I think the photomask industry, the two companies that dare to try to project what's going to happen, there's Semi and Tech Insights. They both have the industry roughly flat, maybe shrinking a little bit, which is a lot better than the broader semiconductor industry. So it looks like photomask will hold up a little bit better than most of the industry, and then start to come back in 24. Although most of the things we've seen and studied suggest that could be a little later in 24 than was originally projected. And so, it's been a pretty good place to be during the current downturn. I mean, our Photronics, if we stay on schedule for this 2023, we'll hit our 6th consecutive year of record revenue. Don't tell any of our customers because we want to raise prices. But if you want to buy the stock, PLAB.
Go ahead.
Aki, this has been a tough year for memory. So yes. 2023 is one of the worst in a long time. And we're definitely in the red section, even on the mask side of the business. We felt the slowdown. We see, memory makers are just cutting back on overall wafer supply into the market. And it affects mask supply. And I'm very happy, actually, to see the broader industry at least saying stay about the same size. Generally, the mask industry doesn't necessarily trace one for one with the semi industry, but on this year we saw impact. Maybe we start to see turnaround here at the end of the year, start to see volumes picking up, and 2024 should look brighter.
Mm-hmm. How about longer term going from
Longer
cyclical,
term,
right? It's a little bit
longer
cyclical.
term, we definitely see demand picking up, especially as we add new wafer fabs, and I think that's not just for Micron. I think that's broad across the industry.
Right.
Forecasting is still difficult to really see on the EUV mask side, like we said, how many copies are going to be needed, and how many layers are going to convert, and how are they going to run 193i versus EUV. These are all difficult questions to see even 1 year out. But long term, we do generally see an upward trend.
Yeah, very optimistic there. Harry?
I think in the world of logic, I think even when there's a downturn, if it's not too severe, the impact is less, simply because the number of masks you make is very much correlated with the number of designs, as opposed to wafer volume, and I think that's going to be not come down too much, even though we have a bit of a downturn. At the same time, I actually see reasons for having more designs. We just know that when you go from a CPU to a gate array to an ASIC, you have energy savings. And in this world where this is a concern to many people, and you think about the scale of things, if you save 10 watts on a chip, it may not sound very much. But on the other hand, if you make 100 million of these go into product, now you're talking gigawatts, and so the impact can be great. And I think that there would be forces like that are going to actually drive more designs as we go forward. So,
Yeah, innovation with electronics is definitely not ending, for sure. So that's good. So thank you. Yeah.